Welcome back. Today we're unpacking the absolute workhorse of the entire plastics industry, White Masterbatch. Now look, there's this massive industry myth floating around out there. A lot of folks assume that making White Masterbatch is, well, incredibly simple. They kind of think, hey, you're just throwing some titanium dioxide or TiO₂ into a mixer, right? I mean, how hard can it be? Well, we're going to absolutely shatter that illusion today. Because the reality, manufacturing a genuinely high-quality White Masterbatch demands an intense amount of precise scientific knowledge. It is a highly sensitive process. If your TiO₂ selection is even slightly off, or your dispersion process is flawed, or you just happen to choose the wrong polymer carrier, the entire product's whiteness, opacity, and processing will completely fail on the factory floor. Okay, let's dive into this. Here's our roadmap for mastering this product. We'll start with the anatomy. Look at TiO₂ as the beating heart, compare Rutile versus Anatase, cover carrier selection, reveal the optical brightener secret, and finish up with processing and troubleshooting.
Let's kick things off with Section 1, the anatomy. So what actually is a White Masterbatch?
At its core, it's a highly concentrated mixture engineered to give you exact whiteness levels, opacity, UV protection, and just an overall enhanced appearance for your final plastic product. Looking at the composition percentages here perfectly shatters that myth that Masterbatch is just 100% pure color. It's not. The active ingredient, the TiO₂, typically makes up anywhere from 40 to 75% of the mix. Then your carrier takes up 20 to 55%. That's basically your delivery vehicle. And finally, specific additives make up that crucial remaining 1 to 5%. And keep in mind, these ratios shift constantly depending on exactly what you're trying to make.
Moving right along to Section 2, TiO₂, the beating heart. If you think of a White Masterbatch as a living, breathing anatomical body, titanium dioxide is absolutely the heart. It's the vital organ, pumping that brilliant appearance right into your final product. And this perfectly illustrates exactly why TiO₂ is so incredibly effective at its job. It all comes down to physics, specifically something called the refractive index. That's just a physical property that measures how much light bends when it passes through a given material. TiO₂ happens to have an exceptionally high refractive index, so when light hits those tiny TiO₂ particles suspended inside the plastic, it bends sharply and scatters immensely. That immense scattering effect, that's exactly what creates that brilliant whiteness and deep opacity. The better the scattering, the better your hiding power. It's that simple.
Next up, Section 3, Rutile versus Anatase. This is a massive industry debate, and making the right choice here dictates whether an outdoor product thrives or totally degrades in the sun. Let's actually put them side by side. On the left, we've got the Rutile grade. This gives you noticeably better opacity and, crucially, vastly superior UV and weather resistance. Because of that rugged outdoor durability, Rutile is the absolute go-to for automotive parts and agriculture films. Now, over on the right, we have the Anatase grade. Anatase offers extremely high brightness and this highly desired, slightly bluish tone. Plus, it's cheaper, but it has one fatal flaw. Its weather resistance is terrible compared to Rutile. So, the overarching reality in the industry today is that despite the higher cost, Rutile is the dominating standard. Outdoor durability is just way too important to sacrifice to save a few bucks.
All right, Section 4, choosing the right carrier.
If TiO₂ is the heart, the carrier polymer is the body holding it all together. And the absolute golden rule here is compatibility. The carrier must seamlessly integrate with your final product. It's pretty straightforward logic, really. If you're making polypropylene, or PP products, you've got to use a PP carrier. If you're manufacturing polyethylene films, think plastic bags or wrap, you use an LDPE or LLDPE carrier. And if you're attempting to formulate a universal masterbatch meant to work across multiple different plastics, you have to engineer very specific blend carrier systems. You always match the carrier directly to the application.
Which leads us to a massive, incredibly common pitfall, the false economy of low-cost carriers. I see manufacturers try to save a few pennies by using a cheap, mismatched carrier all the time. And what happens? It immediately leads to poor dispersion of the TiO₂. That clumping results in ugly surface defects and noticeable shade inconsistencies across the entire product run. You literally end up ruining the final appearance and wasting far more money in scrapped product than you ever saved on the cheap carrier. Don't do it.
Okay, let's get to the fun stuff. Section 5, the Optical Brightener secret. This is where we cross over from a standard, dull plastic to a truly premium, high-end white. So, I want to pose this question directly to you. How do you actually make white look premium? Because if you just take a standard mix of TiO₂ and polymer, it's usually going to have this slight natural yellowish undertone to it. It just doesn't pop. To fix this,
Chemical engineers literally pull an optical illusion on the human eye.
They pull this off using an additive called an optical brightener, or OB. And the step-by-step physics of this is just fascinating. Step 1. The optical brightener sits in the plastic and absorbs invisible UV light from the surrounding environment. Step 2. It takes that trapped energy and actually emits it back out as visible blue light. Step 3. That emitted blue light scientifically cancels out those natural yellow undertones in the plastic. The final result? A brilliant premium white that literally glows. But, and this is a critical rule you have to remember, optical brighteners improve whiteness. They do not improve opacity. They make your product look much brighter, but they aren't going to help you hide whatever is underneath. Finally, let's bring it all down to the factory floor with Section 6, Processing and Troubleshooting. Because let's face it, having a perfect formulation on paper means absolutely nothing if you can't process it correctly in the machine.
To achieve perfect dispersion and dodge those devastating visual defects, these processing parameters are non-negotiable. You have got to maintain a proper temperature profile. If it's too hot, you degrade the polymer, too cold, and it just won't mix properly. You absolutely need the correct screw design in your extruder to create the exact right shear forces. You need adequate mixing time. And, maybe most importantly, you must maintain strict moisture control. If you ignore any of these, you get terrible dispersion. And that manifests on your floor as ugly white spots, uneven streaks, and horribly low opacity in your finished product. So consider this your screenshot-worthy cheat sheet for reverse engineering common floor failures. If you're pulling a product that looks yellowish white, your culprit is almost always polymer degradation from excessive heat. The fix? Lower your extrusion temperature right away, and maybe consider adding an optical brightener. If you're dealing with low opacity, well, that's usually just low TiO₂ loading or poor mixing. You solve that by increasing your TiO₂ levels or improving your mixing parameters. And lastly, if you're seeing white specks, that means your TiO₂ is agglomerating, it's clumping together. You're going to need a better dispersion additive package, and you'll need to re-optimize your processing speeds. Which brings us nicely to the core thesis of this entire explainer. Quality cannot be judged by TiO₂ percentage alone. Look, anyone can just dump 70% titanium dioxide into a mixer. But true professional formula development? It's a delicate, scientific balancing act. You're constantly weighing maximum whiteness against perfect opacity, flawless dispersion, manageable costs, and seamless processing performance on the floor. So as we wrap up, I want to leave you with this provocative thought regarding your own manufacturing processes. Are you formulating for just color, or are you truly formulating for performance? Understanding the complex science behind the TiO₂, the carriers, and the processing is exactly what bridges that gap. Thank you so much for joining me today to unpack the hidden complexities of White Masterbatch. I enthusiastically invite you to join us next time for another explainer, where we're going to be doing a massive deep dive into Black Masterbatch. We'll be exploring carbon black selection, the secrets of jetness and undertone, and exactly how to troubleshoot dispersion problems on the dark side of the spectrum. See you then!
So today we learned that advanced color correction is not just about adding pigment, it's about understanding LV value, delta E processing conditions and real production challenge. But here's something interesting. What if your spectrophotometer show a perfect color match, yet the customer still reject the part? Yes, it happens more often than you think, and the reason might surprise you. In the next video, I will reveal a real industry case study where color matching looked perfect in the lab but failed in production. If you want to master color matching, troubleshooting, and practical polymer industry knowledge, make sure to subscribe, hit the like button and comment below. Color expert. See you in the next video with another real world color challenge. Thank you.